So in the previous lecture, we have looked at different ways of writing irreducible representations. We have just mentioned different ways of writing irreducible representation, and one of the ways was unit vector transformation. So let us finish on that. So the two types of unit vectors we have seen was a linear set of vectors, which are unit vectors along x, y, and z axis, right? And then the second set we have seen was the rotational vectors, which are anti-clockwise rotation of x-axis when visualized from positive side of the axis towards origin. Similarly, we have ry and we had rz. So we can see that the effect of symmetry operations onto these vectors gives rise to irreducible representations. For example, we saw the case of C3V, where I'll not write all the elements, but so for example, we saw, let's say if we take tau xyz, where we are doing operations onto xyz basis, we saw that we can form a 3x3 matrix, and then similarly if we do it for C3, we saw again it can give us 3x3 matrix, and then this can be block factored into 2x2 and 1x1, right? And similarly for sigma v and so on, we can observe. So this, upon block factorization, gives you tau 1, which is of 2x2 order, and tau 2, which is of 1x1 order, and both are irreducible representations, right? So this we saw. So now let us see. So although it is easy to visualize the effect of operations onto x, y, and z, but effect of operations onto rx, ry, rz is little, it's not as trivial as x, y, z. So let us see certain thumb rules which actually help you to see the effect of operations onto rx, ry, rz. So thumb rules for unit vector transformations. So effect of rotation. Let's first look at effect of rotation. So character is represented by chi. Character can also be called as, if it's 1x1 element, it is trace of the matrix element. But if it is more than one dimension, then it is strictly trace. Or we can say a particular matrix element. So let's just call it as character of C and Z when C and Z is operated upon X, Y, Z or Rx, Ry, Rz. This character remains same. So that means if you are operating C and Z on X and you are operating on Rx, result will remain same. If X goes to positive X or negative X, Rx will also go to positive X or negative Rx, right? So if, for example, if we are doing C and Z on X, it will go to minus X. So that means the character will be -1. And so similarly, if we are doing C and Z on Rx, it will go to minus Rx. So character again will be -1. So the effect of rotation, the character of C and Z remains same whether you are doing it on XYZ or Rx, Ry, Rz. So that is easy. Now for effect of inversion. So character under I inverts X, Y, Z and remains same for Rx, Ry, Rz. What does it mean? So if you are doing a inversion operation, so X goes to minus X, Y goes to minus Y, Z goes to minus Z. So character inverts under X, Y, Z. So that means you will get -1, -1, -1 as a character, whereas character under I will remain same for Rx, Ry, Rz. That means Rx will remain same as Rx, Ry will remain same as Ry, Rz will remain same as Rz. So that means the character will remain as plus plus plus. So plus 1 plus 1 plus 1. So that means the character under XYZ is opposite to the character under RX, RY, RZ. Okay, so that is easy. Now let us look at the effect of reflection. So let's say these are the basis sets RX, RY, RZ, and these are the operators sigma XY, sigma YZ, sigma ZX. So again, if we are talking about any other sigma which is not oriented along the axis, then you will have to calculate the new axis system and then do all sorts of maths. But it is easy if you do only for sigma XY, YZ, ZX. Okay. So now let's see what happens here. So XY, if you are doing, X and Y remains as X and Y. So the character will be plus 1, Z goes to negative. And it's quite the opposite here. So Rx and Ry will be reflected as negatives and Z will remain positive. Similarly for YZ, it is X which is negative 1, 1 and X which is positive minus 1, minus 1. So you see that again it is opposite for reflection. ZX will be positive for this and negative for this, and then it will be positive for this, minus and minus 1 here, right? So effect of reflection is also easy. Now effect of improper axis. So character of SNZ for Z is opposite of RZ. So typically if you see that the character under SNZ for Z is equal to minus 1, right? But for RZ it will be plus 1. Why is that? So you can see that SNZ is actually CNZ into sigma XY, right? So if you are doing CNZ operation onto Z, it will remain as Z. If we are doing sigma XY onto Z, so onto Z, so this will be 1 into minus 1, right? So this will come out to be minus 1. Whereas if we are doing onto RZ, so CNZ on RZ, so if you are doing on RZ, so CNZ on RZ will remain as same, whereas sigma XY on RZ, so sigma XY, so we can read from here. So if you see sigma XY on RZ, it is positive 1, right? So it is actually positive. So you will get product as positive. So this will be opposite of the two, right? So a character will be opposite for Z and RZ. Okay, so that is easy. So now also you can use this to generate irreducible representations, but we will see in different examples when you do it, it will not be generating the complete set of irreducible representations, and hence we have to resort to something called as great orthogonality theorem. So let us look at what that is. So great orthogonality theorem. So let me first write down the complete statement and then I will try to explain what the theorem states. So let us look at the definition. So in the set of matrices constituting IR representations, any set of corresponding matrix elements behaves as the component of a vector in h-dimensional space such that all such vectors are mutually orthogonal and square of its length is equal to h by li. So let us look at one by one what does it mean actually. So it's a complicated statement, but let's take an example and see what does it mean. So in the set of matrices constituting IR representation, so let's take the case of C3 point group, because we have seen the matrices there. So let me write down all the class elements expanded, because here we are dealing with the matrices. So matrix for different, even if the trace of the class elements are same, the matrices are different, right? So I'm not going to write the complete matrices. I'll just mention, I'm mentioning this point because it is important for this theorem. Okay. Now let's write down first irreducible representation, which is of 2 cross 2 matrix. Okay. So I'll just write down all the matrices, and I will mention that these are the corresponding elements of the matrices of a given irreducible representation. So for example, in a 2 cross 2 matrix, you will have 4 elements. So I'm just giving a color code to all the corresponding matrix elements, because it talks about the corresponding matrix elements here, right? And then let's choose one more color. So you have, okay. And then let's also write one more irreducible representation for 1 cross 1 matrix. So in this case, the matrix element is only 1, right? So if you are talking about corresponding matrix elements, it means only one element basically, which is given by this color over here. Okay. So we have seen, so set of matrices constituting IR representation. So these are the set of matrices which are constituting IR representation. This is one set, this is another set, right? So, and we have also seen what is the corresponding matrix element. So these are the corresponding matrix elements for one particular set. Behaves as the components of a vector in h dimensional space. Okay, so now what are the components of a vector in h dimensional space? What does it mean? So let's start with a simple case of 3-dimensional vector. So 3-dimensional vector is represented by, let's say, x, y, z is the coordinate of that vector, and if the vector length is r, so you can write this as xi plus yj plus zk, right? Where I, j, k are unit vectors along x, y, and z dimension, right? So x, y, z are the components of a vector in 3-dimensional space. This is a 3-dimensional space where x, y, z are mutually orthogonal to each other. Now here we are talking about h dimensional space. So what is h dimension here? H dimension is nothing but order of this group. And we are saying that the corresponding matrix elements, so let's say if we are talking about these matrix elements A1, A2, A3, A4, A5, A6, so these form a vector. Let's call that vector as A, A1i plus A2j plus A3k and so on. Okay, so here h is the order of the group, so order of the group is 6 here. So in this case it is in 6-dimensional space. These are the components of the vector. Okay, so all these matrix elements form components of a vector in h-dimensional space such that all the vectors are mutually orthogonal. So when I say mutually orthogonal, what do I mean? If I take another vector as b vector, let's say I call it as b1, b2, b3, b4, b5, b6, then my b is nothing but b1i plus b2j plus b3k and so on, because it's a vector, so I'm just writing caps, where caps are unit vectors along these dimensions EC3 and okay. Now when I say that these vectors are mutually orthogonal, that means my a dot b is equal to 0, right? That's the definition of orthogonal vectors. So if these two vectors are mutually orthogonal, the product of these two components and the summation over all operations will go to 0. Okay, And then square of its length, if I talk about square of its length, then the square of the length of this vector is nothing but a1 square plus a2 square plus a3 square and so on, will be equal to h by li. So if I write mod of a, it will be h by li. What is li here? Li is the dimension of the given irreducible representation we are talking about. Okay, and then h is the order of the group. So in this case, let's say if we are talking about tau 1, so for tau 1 h will be 6. H will be 6 for any tau here, but li will be equal to 2 for this tau 1, right? Okay, so that makes sense. So now this orthogonality theorem does make sense, that any component of this corresponding matrix elements form the components of a vector in h dimensional space, and these vectors are mutually orthogonal and they are normalized. We can write here normalized such that square of its length is equal to h by li. So now let us look at, now that we have understood the meaning of this theorem, so let us see how to write this theorem in mathematical form. So let's see how to write it up. So if I have summation over all r, because we are summing over all the symmetry operations, so r here is the symmetry operation. So we are taking summation over all r, and we are talking about tau I r m n and tau j r m prime n prime, and then we have to take complex conjugate of this. If we are dealing with complex numbers, then one of the factor here in the product will be complex conjugate. You can take complex conjugate of any of these, it does not matter. Okay, so this is equal to h over li lj, and this will be delta ij delta m prime delta n prime. Okay, so let us look at the meaning of all of this. So r is symmetry operation. Okay, so we have seen, so this is summation over all symmetry operations. M and n are indices of various matrices, right? So mn represent basically mth row and nth column of a particular matrix. Okay, and then tau I is ith irreducible representation. Okay, so tau j is jth irreducible representation, and so on. H is order of the group, we all know that, and li is dimension of ith ir representation. Okay, or we can say dimension of tau I. What do you mean by dimension? Dimension means the size of the matrix. If the matrix is 1 cross 1, li is 1. If the matrix is 2 cross 2, li is 2, and so on. Okay, now deltas are Kronecker deltas. Delta is Kronecker delta. We all know what this means. It takes the value as 0 if I is not equal to j, takes the value as 1 if I is equal to j, and same is for mm prime and nn prime, right? Okay, so now let us quickly look at the orthogonality condition and the normalization condition. Okay, if the vectors are chosen, so we know what vectors we are talking about now. If the vectors are chosen from matrices of different IR representations. Okay, so that means then we say that they are orthogonal. So we saw the example of a different IR representation, that is tau 1 and tau 2. If we are taking the matrices vectors which are formed by components from different IR representations, then these will be orthogonal. So that means this implies that I is not equal to j. The moment you say that I is not equal to j, the right hand side goes to 0, right? And what happens to left hand side? Left hand side remains same, right? There is no change. So what we had will remain same. So tau I r mn, tau j r m prime n prime, right? Now let's say if the vectors are chosen from same IR representation, if the vectors are chosen from matrices of same IR representation, they are still orthogonal. So in this case, we are talking about m is not equal to m prime, n is not equal to n prime. So that means we are talking about the product of which two matrices? Matrices which are formed by this vector and this vector, for example. Okay, so this set of vectors and this set of vectors, or this and this set of vectors. Okay, so in this case your m and m prime and n prime will not be equal. Okay, so again, due to delta mm prime and delta nn prime, you will again see that the right hand side will be equal to 0 and the left hand side will remain as same. Okay, now the normalization condition. So for normalization, what we had, I is equal to j, we have to take from the same product. So normalization condition means that you are taking a product of a1 with a1, right? So I is equal to j, m is equal to m prime, n is equal to n prime, because we are multiplying the same vector twice. So this means that you have I equal to j, m is equal to m prime, and n is equal to n prime. So this implies that you have summation over all r tau I r m n. This is my first, and then the second is also same, so this goes as square, right? And then this becomes h upon li, right? So this is the mathematical meaning of what we just explained using C3V point group example, and we saw that how these vectors are orthogonal and normalized. So in the next class we will see different properties of this GOT, that is great orthogonality theorem, and then how these properties are actually used to deduce irreducible representation without having to worry about what is the basis set, what is the effect of symmetry operation onto the basis set or onto the molecule also. So we'll not worry about all of this. We'll just take a point group, pick up a point group, and then write down the irreducible representation by doing the maths defined by great orthogonality theorem properties. Okay, so that's all for today. So see you in next class.